Okay. So let me show you, though I can do screen share as well, but perhaps this works better, as screen sharing usually would cause some, it's not that smooth. So uh, here is the discrete Fourier series. It's an animation you can find on YouTube, and if you search for Fourier series animation, it'll show you, and there are many animations which you can find on YouTube, and I would urge you to go on YouTube and find out all these animations so that you have, you conceptually understand the Fourier series and what it really means. So this is like, it tells you that Fourier series of a square wave will have a fundamental harmonic, and then you start seeing, like, once we have 2 and 3 and 4 and 5 and more and more and more, and there are always multiple of the fundamental frequency, and how they shape up all together, coming together, they shape up into a square wave. And same you can find for triangular wave. And so this is the fundamental harmonic. So what you see is the fundamental harmonic, and so this is as this is a circle which is exactly producing the second harmonic. So you see now it is taking the shape of and definitely you got to figure out the phase and the amplitude. So this is the third harmonic, okay, and this is the amplitude. The circle shows the amplitude, and the way it rotates shows the frequency. Now this is the third harmonic, and I just keep adding more and more and more, and surely it start taking the shape and of a square wave as it adds more and more and more of the harmonics. And so this is what the Fourier said, that any periodic signal can be split into a number of sinusoids, and as you can see, add more, so you get closer and closer to the shape of the signal. And this is the top mathematicians of his time would not actually comprehend and understand and appreciate that this could actually happen. And so Fourier series and discrete Fourier series is even more interesting, as I mentioned. And discrete Fourier series, you have exact number of cosines, so to say, or exponentials, which can add up together and make the shape of the signal. So this is something which I wanted to show. And then is let me quickly go over two things. One is what we have studied, which is so this is the same thing. If you go, there is a simulation which basically would construct a triangular periodic signal as well. It's beautiful. You see how so many of these would shape up into a triangle. Square still we can comprehend, but making them into a triangle is amazing. Like first harmonic is like the triangle you see in blue color. We have studied that a periodic signal. So a periodic signal is important. This is how a periodic signal is represented. It is a periodic signal which is at every capital N it repeats itself. Every capital N it repeats itself. Okay, so this is a periodic signal, and then this can be split. The periodic signal can be split into n complex exponentials of different magnitude and phases. So the summation means you add all exponentials together, it'll make you the periodic signal. Okay, so this is important. So n different frequencies, important is n different frequencies. Usually in this book it uses, which is okay, I don't mind that it uses it uses W for this exponential instead, because it's very cumbersome to write this exponential again and again. So book finds a simple way that it writes a W n k n. So in many research papers, instead of exponential, you will find this W. And because this book by Oppenheim and Schaeffer is primarily, you can call it a Bible of signal processing. They are the people who actually invented signal processing, like Schaeffer and Parks, Dr. Schaeffer and McLaughlin and all these people. They actually invented signal processing, and once I took a course from them, and they would actually tell you why they use W, why they put a tilde, why they call this K, and the notations they use, and they would actually tell you all about the rationale for actually using this terminology. So two formulas, one is for the analysis and the other one is for the synthesis. So we know that. So two formulas, an analysis and for the synthesis. So this is the same formula. Okay, and now as I have already told you the rationale of studying discrete Fourier series, because of this resemblance of these formulas with discretization of discrete time Fourier transform formula. So this is okay. And this is a question which I would like Dr. Ali to actually solve in the next class. So that's why I did not solve it. So he will solve it for you, that it's a periodic signal. It's a square wave, a little different in character though. So it is this and then it remains 0. Then it is this, then it remains. So it's a square wave which runs like this. So wave, okay. So it's a digital square wave. A digital square wave, and you use to find out discrete Fourier series. So you use the formula, you use the summation, and these are the coefficients. Means it has a DC value of worth 5. It has first harmonic of this amplitude. Then it does not have second harmonic. It has third harmonic, but it does not have fourth harmonic. And then it repeats. The coefficients are, because its period is 10, so after 10, you see the coefficients will repeat themselves. And like Fourier transform, you will also see the symmetry, like evenly symmetric the magnitude and odd symmetric the coefficients. And once your magnitude is 0, you are not interested in phase. Obviously something which has 0 magnitude, the phase is not interested, because there is no phase, amplitude is 0. So these are the properties which we studied, like the linearity property. And remember, I said if you multiply this with A, so you multiply this with A, you multiply this with B, you multiply this with B, and once you add them together, so you get this. This is the linearity property of the discrete Fourier series. Then shift in time and shift in frequency. A circular shift in time is multiplication by an exponential minus j 2 pi k over m. Okay, this is circular shift in time. Or the other shift is that if you multiply it with an exponential, okay, with an exponential, and then it is a shift in frequency. And this is the duality. So the duality property is also important, that you take discrete Fourier series, you get this answer, and you again take discrete Fourier series. So you're going to, because this is also periodic, so you get the same signal circularly shifted and multiplied by n. So we have seen this. Then is the important property, which is the convolution property, which says that multiplication in frequency, this is circular convolution in time. So this is the formula for circular convolution, which I told you earlier. So computing circular convolution is very cumbersome. And why? Because you have the signal, okay, this you are keeping as is, or you shift one of these signals, you keep this as is. So this is, so you are asked to perform circular convolution of these two signals. So you decide to keep this as is, and this you circularly shift. So how do you circularly shift? By these will come on this side. So you say this is the circular shift of this signal. Okay, so circular shift of the signal, you can see it here. And then you multiply them together, each sample together in this window, and add them up together to get an answer. And then you shift. So this is shift by 1. This is shift by 2. And repeat the same operation. Shift by 1, shift by 2, shift by 3, shift by 4. So this is one way of performing convolution, that you have shifted version of this. Okay, you have shifted version of this, and then you are basically multiplying them together to get one answer. Then you shift it by 1, then you shift it by 2, and you get these answers. So this is one way of actually performing convolution. Now we come to discretization of the formula, which is this, and I told you the two reasons why we want to discretize this formula, and the reasons are that two reasons. One is this computer cannot handle infinite amount of data, and the second reason is that this omega is a continuous variable. So you got to deal with both, and once you deal with both, you get to a formula. So you're dealing with both. So dealing with both will require you to primarily discretize omega into 2 pi divided by n parts and k. So it has a relationship with Z transform as well. So this is the Fourier transform. Z transform unit circle is Fourier transform, and then on discrete points is the discrete Fourier transform, and this is the formula. And the problem with the formula is same, that it's the same formula as was the formula for discrete Fourier series formula. So these are the two formulas which are the same as, or sometimes you write W, as you know. Usually the book also write an N here. Okay, an N here. So these are the analysis formula and the synthesis formula, which is fine. This is very important picture which I have shown you earlier as well, that this tells you the power of discrete Fourier transform. That sometimes why we use it, because in many applications the information what you intend to see is hidden in the frequencies. So you want to convert that signal from time domain to frequency domain, as is done here. The signal you first convert, you take its FFT is not shown, and then you only take 2.5%. This is just amazing. Like if this is an image of this size, you take only very little part, which is 2.5% of the whole image, which you get after taking FFT. And then you throw away rest of the image. So you throw away rest of the 2D signal, which is FFT, and only take inverse of this. And look, you still get an image which you can easily recognize of that of a joker. So the power, and this is what is used in all your modern day cameras. A technique something similar to this is used in your modern day DSLR cameras and your cameras in the mobile phone, that they can actually do this in real time. Once you click, and they are not taking the raw image, they are taking an image which is actually stored in a very different format. It basically takes a kind of FFTs, and then once you visualize it, only then it takes inverse and show you something like this. So it's important that and you can always prove that this is periodic by replacing n by k plus n. So it will give you the same answer as we have done in discrete time Fourier transform. So we have covered all of this. This is periodic. And then these are the problematic areas, like which I already told you, that once you are dealing with discrete time Fourier transform, it changes the character of your time domain signal. It assumes it as if it is a periodic signal. So all these properties, even the duality property and the shift property, and this is what the book does. What book uses a very kind of bit complex notation. So if you are shifting it by m, so it'll put an n here, and this n means that please consider this as a circular or a periodic signal. So a shift should be a periodic shift, and then you can apply this property that a shift is multiplication by an exponential, as is done here. So what the book does is it says you have a signal, you make copies of it to make it periodic, change the character of the signal, and then you shift the signal. Okay, so you are not shifting this signal, you are shifting the periodic signal. So you get this answer, and then you throw away this. This is going to be your answer. So you don't like this answer because you want to actually do the linear shift, but the linear shift has not happened. What has happened, if you are basically multiplying a Fourier transform with an exponential, what is happening is it is translating into a circular shift, and you have absolutely no interest in circular shifts. This is important for us to understand. I have absolutely no interest in circular shifts. So same is the properties for multiplication by n. This is the circular shift which I have just told you, that how you perform circular shift. Another example of circular shift, and so circular shift example. Duality, we have covered that. What is duality? Circular flip is also, if you want to do a circular flip, one method is what I told you: draw a circle, put values in clockwise and read values anti-clockwise. That will give you a circular flip. But if you want to use another method, it is here. You have a signal, then you copy it here and here, and then you flip. So all this part will get a mirror image. It will come here, this part will go here. So this part, as you see, all these zeros will come here, then these two values, then these three. So this is a circle, and then you throw away these, so this will give you a circular flip. So a circular flip can be calculated in these two ways, and the most important is the circular convolution. And I've told you how to perform circular convolution by basically circularly flipping and circularly shifting one, keeping the other as is, multiply them together, and then just keep repeating that. It's very, very cumbersome. If you are asked to actually do this, these are the steps you have to take. If I ask you to perform circular convolution of these two signals, and please remember, I have no interest in performing circular convolution. I have only interest in performing linear convolution. But unfortunately, if I'm using a discrete Fourier transform, okay, then I have no other option but to actually what my multiplication in frequency is doing, that it is performing a circular convolution. So the answer I get will be a wrong answer, and this is what it will be performing in time domain, that you have this signal, so you make copies, then you make circular shift, now you multiply them together, start computing value, then shift, then shift, then shift. So every time you are shifting, and you perform circular convolution. Okay, so this is how the circular convolution is computed, that any sample that goes out will come back here, any sample that goes out will come here. So you can see another method is that you first do the circular flip, and then this sample next will come here, and this sample going out will come here. Okay, every time the sample goes out will come back in the window to get you the effect of the circular shift. So this is just another example I put in here, but I love this way of actually performing circular convolution, that one signal you write counterclock, the other signal you write anti-clockwise, and then just keep rotating this. And so this 0 is here, then this 0 is here, then 0 is here, then 0 is here, then 0 is here, then here, then here, then here. So you perform this spread xn, spread clockwise, spread yn, counterclockwise, multiply them together, get an answer, and that is the way we should actually compute this. And this is just a simple code I have written to actually show you that this is how, as I told you, there are two loops. This is one loop and this is another loop, and you are computing the 2 pi kn over n. I'm using I and j using the exponentials, and then this plus plus plus, and this will just, so perhaps again 10-15 minutes a good programmer can write a program to compute discrete Fourier transform. So this brings me to show you something in MATLAB. So now the issue with discrete Fourier transform is that that is the only way for you to find out Fourier transform. Okay, and the convolution would change its meaning. That if you are using, I don't know how to. Let me just do this in a while. First, let me just what I said, that there is a topic which is not part of the course, but still I want you to know this topic because these are the amazing things people are doing in signal processing. This is Parkes-McLaurin algorithm. Actually, I started working for my PhD with Dr. McLaurin. For a while, I worked with him, and there was some issue of funding. Then I switched to another supervisor. But he was this great guy who actually invented an algorithm which is known with his name. Though he was very humble, he called this Rimas exchange algorithm, but in many books it is known as Parkes-McLaurin algorithm. Okay, so Park was his supervisor in Rice University, and McLaurin was, and then joined MIT, and then he came to Georgia Tech and stayed there. I think he's still there. So this is an algorithm where, again, it is his PhD thesis, so must be very complex. So I am not really interested in just going over this in our undergraduate course. But what he tried doing is that he said minimize the maximum error. So this was the thing which he said, minimize the maximum error over a set of closed intervals in frequency domain. He said this is your desired response, okay, and this is your response, that you can weight them, and this is your error. And instead of minimizing the error, usually we engineering, what we do is we minimize the error. He said let's not worry about the error, total error, let's worry about the maximum error. So this is this is my desired response, as we know. This is my desired response. So he said, find out where is the maximum error. Okay, so where is the maximum error, and you try to minimize this error so that the ripple side basically reduces the tolerance, and that is what we care, because once we are designing a filter, important is deltas. Okay, and not that how many time it ripples and how this frequency response live in this band. Important is that this range is important. So he said let's try to minimize the maximum error, and his algorithm will do iteratively solve this and will give you an h of n that actually minimizes the maximum error. Okay, so this is what the Rimas exchange or Parkes-McLaurin or equiripple, so it is known by different names. And I'll tell you the strength of this. Again, it is not included in the course, but once you are designing algorithm, it is important for you to know that there is an algorithm which gives you the best, almost the best option for designing your filters, and it is the Rimas exchange or equiripple algorithm. Okay. So in MATLAB, once you are designing your algorithm, we know that, or designing a filter, and we have spent a lot of time in learning about these, that this is the filter design toolbox. You can design an IIR or you can design an FIR filter. So once you're designing an FIR filter, and we know that you can use Windows method, so this is the Windows method. Okay, so use a Windows method to design an FIR filter, and you say design filter. These are the specifications, 80 dB down, and the cutoff frequencies and everything. So once you do this, it is telling you that you need to have 101 coefficient filter. Okay, this is an FIR filter. A good response minus 80 dB is the stop band ripples, and you can actually go and look the impulse response, which definitely is going to be a sync. We know that and this is a Kaiser window method, and it gives you a sink but 101 coefficient filter, means every output you require 101 multiplications and 100 additions. So quite an expansive filter, going to have 100 zeros, and you know that they will be in cluster of 4 if they are not on the unit circle, so cluster of 4, and all these zeros are going to keep them below 80 dB. And so this is one method. So but if you go here and say I don't want Windows method, I would rather use least square method, which is the Parks-McLaurin algorithm, least square method, and you say design me a filter. Least square method, design me a filter, and it'll just do, it apparently has changed the stop band. Let me see, we want to have, so it has changed the specs. I think it was 80 dB here. So equiripple, the least square method or the equiripple method will actually design the same filter in almost half of the coefficients. If you do that, it's amazing that it will only take it 50 coefficients to design the same filter. So once you are designing FIR filter, it is best to use the least square method of designing filter, and because the least square method gives you the best filter design. Okay, so it's just taking some time, but this is, oh sorry, this is the problem. I have here minimum specify order, but you can do it yourself. That if you do that, you design a filter which would only take the minimum order using the least square method of filter designing. Lab is stuck. Session no. I may go to the app and do the signal processing and filter design. I say close. I say equiripple and the same filter. Okay. So you see 50, only 50 coefficients, and the filter is minus 80 dB down. So the same filter that we were designing using a windowing method was taking 101 coefficients. So it's amazing, like how can like an algorithm cut the number of coefficients into half, as Kaiser window was supposed to be the best window to design a filter. So this is what I intend to show you this. And the second thing, which perhaps we will spend more time in the lab, but still let me just generate a signal. X is equal to 1 1 1 1 0 0 0 minus 1 2. So this is a signal which is 4 5 6 7 8 9 coefficients, 9 samples. Then you have an edge which is minus 1 2 3 4 5 1 2 3. So 1 2 3 4 5 6 7 8 and 9, for example. These are the two signals. Okay, so these are the two signals. I have this X and the Y, and I want to convolve. There are two methods. One is to use the DFT method. So let me use the DFT method of finding FIFFT of FFT of X dot multiply FFT of H. Inshallah, we'll spend more time in the lab, but this is the answer. If you see, this is what I told you earlier, that multiplication in frequency is actually circular convolution. So if you perform circular convolution of these two signals, you will find out that you are going to get these values, which is 14, 15, 16, 7, 34, which is not same as performing the linear convolution of h comma x, which are these values. Okay, so you find that these values, this is the answer of my linear convolution, and this is the answer of circular convolution. All values are different. -1 it is 14, 1 it is 15, 4 it is 16, 8 it is 7. So I get a wrong answer, though I am using that property which says convolution in time is multiplication in frequency, but I am getting a wrong answer. So this is very problematic, but I want this multiplication to give me a right answer in time domain. Okay, so we need to figure out a way where this multiplication in frequency should give me a correct answer, and we are going to spend some time on this, and then we will be left with just one topic, which is fast Fourier transform, and we will see that what we do with that, and after that we will be done with the course. We may just still, there are things which we can always discuss, but I intend to take an assessment. I don't know, should I take it now or should we postpone it and do it in the next class? I think let me postpone it and we do it in the next class. So in the next class, I will take an assessment, and kindly make sure that all of you are present, because I'll give you perhaps in the start, I'll give you the assessment. So we'll do the assessment. Okay, not now, sure. Okay, next class is fine. Next class, okay, no problem, next class. So we take that assessment from in the next class, and Dr. Ali will also will be signing, solving some of these problems, inshallah. Okay, thank you very much. Oh, somebody is saying now. Oh, it's now again. So there are people who wants to do it now. Now, next class or never? Okay. Okay, he's ignored. Okay. No. Okay, thank you. Inshallah, see you next time. Bye. The assessments. Now whole class will take next class. Okay, Hamza, I'll send you the assessment. Huzamas, I'll send you an assessment. Okay, I'll inbox you the assessment. So solve it and send it back in 5 minutes. And rest of you enjoy your life. Thank you very much.